Okay, so the end of that last video was really crazy, and I need you to stop right now, go back through that last part, and really think about what I was talking about and how these models work. How we're trying to have the data that we have observed and what we're trying to estimate, and we need more data that we know than what we don't know in order to get these models to work. Okay, so we have specified a model, we have identified a model, we now need to estimate a model. And for this class, we are going to use maximum likelihood. There are other things that you will hear about and see. I highly encourage you to look into those as you have time, but we're going to use maximum likelihood. It's the preferred estimator for SEM. It's the most common. You see it in pretty much in most publications. It does require large samples. You have to have multivariate normality, but you can break a lot of assumptions and still use this. What we're doing is we're trying to identify parameters that are the most likely to give rise based on the observed data. And so likelihood you can kind of conceptually interpret as probability. And it's an iterative process to get the maximum log likelihood. You can think about it like this. So we start with a bunch of guesses about a parameter. So we have this model that we have created, and we guess about where the parameters might be. And then we do another iteration, and we see, is that a better fit with the new parameters, these new values? Then we do another iteration. Is this better? Another iteration, is this better? And so we start with our nice clean data, and then we do lots of iterations, and then we see how do we get to stop turning things until everything looks the same. And so we keep doing iterations until we're not finding anything better. And that's when the log likelihood stops and we reach our maximum. Here's a picture conceptually of what it's trying to do, that we have lots of different variations. Some are better than others, and so we're trying to kind of climb the hill to the best possible likelihood or probability of success, and it just stops there. You can see here that we have two that are really close to each other, so we have two potential models that are really close. And it picks what it thinks is the best one, and that's the output that you will get, is the best maximum likelihood of matching your theoretical model, so that implied data set and matrix, with your observed data. We are not going any more in depth with that. If you want, there are lots of things that you can read that are posted, but this class is focused more on the interpretation and the application of the models, and not all of the kind of math and behind the scenes on how to get the models to work and get the math behind it. We're going to just trust that these models work. We're going to trust that all of these programs are done really well. And we're going to be focused on the application and interpretation. So now that we have an estimated model, we're going to start looking at model fit. So pause and read this. So there's no true model. And that means that we have created this model based on what we think is happening, and we've got some theory to support it, and then we get some data that are proxies about the variables that we want to see, and we see how it works. But I could take a data set that's the same data set, and I could draw multiple models with it, and they might all fit just as well. And so just because a model fits to the data doesn't necessarily mean it's meaningful. We're not talking about effect size. It's not like, oh, this is such a great thing, this is a huge impact. It just means that the data support the theoretical model that you drew. It doesn't mean that that model is true or correct. You could have multiple models with similar fits. You could have multiple models and one has good fit and one has bad fit. When we start thinking about classical test theory versus item response theory, in IRT, specifically Roche, the model is held as true. So if your data doesn't fit the theoretical model of Roche, your data is bad and it's not working. In classical test theory, if this model that you have drawn doesn't fit, then the model is wrong or bad, and the data is viewed as true. So you would change your model and see if the data maybe fits better. So since there's no one true good fit, we're going to use 3 different indices to estimate fit. One of them is statistical fit, so where's their chi-square goodness of fit comes into play. We want this to not be significant. Essentially, we want our theoretical matrix to match our actual matrix in a non-significant way, would be an easy way to think about that. But sample size have to be large, and it's really sensitive to sample size, so it's probably going to be significant. Just report it. Absolute fit compares the difference between your proposed matrix, so our theoretical matrix, and our observed matrix to see the difference, and they're trying to minimize that. Relative fit does kind of the opposite, and so it tries to see, does the null model, the baseline model, does your data fit better than the baseline model? Is it better than the predicted model? So for absolute fit, these are 2 that I recommend. I typically report RMSEA. Less than 0.10 is acceptable, but really it's less than 0.8 if you want to get published, and less than 0.08 and less than 0.05 is even better. So I would report a chi-square, and then I usually pick RMSEA. Relative fit, there's a lot of different things that you can look at. I tend to do CFI, and I see that reported a lot. I'm seeing TLI a little bit more as well, but for all of these, above a 0.9 is indicates a good fit. So I would do chi-square, RMSEA, and CFI to report. When we think about how these are being measured, you can kind of think about it like this. If this is the perfect fitting model, so the data fits the theoretical proposed matrix beautifully, versus it doesn't fit at all. There is nothing about this matrices that even come close to fitting the way that you drew them. Absolute fit measures from the perfect fit over, and relative fit operates as a null model, and it says, is it better than this? And it works that way. So take a minute, go back to your guide, and reflect on model fits. Last up is model modification. So we have specified a model, we drew a model, we made sure it was identified, that it would run, we estimated it with maximum likelihood, we have looked at the model fit, we're going to start looking at all of the different things that fit and how things work within the model, and then we can do model modification if we want to. So the goal here would be to improve the model. These are all done post hoc. So you have come up with this really important theoretical model, and you have now found that it doesn't fit as well, or something isn't significant, or items don't load onto factors the way that they should, and you're like, if I got rid of this stuff that didn't work, I bet I could get a better model. The problem with that is that you drew that model in the first place based on theory and logic and lots of rationale, and now you're like, actually, I'm just going to change this. And a lot of times these can be capitalized on chance. So you really need to replicate with a new sample and see if the new model modifications still work. In Amos, there is a modification indice. You are welcome to click this and play with it. I don't usually, because a lot of times the way they improve fit doesn't make sense conceptually. For example, it likes to correlate error terms in the model, and then your fit goes up. But conceptually, why would the error term on A relate to the error term on B? If I don't have any strong rationale for that, how do I rationalize doing that just to make my data fit better? And you have to also remember that SEM is doing two things at once when we get into the big models. You're looking at a measurement model and you're looking at a predictive model. So if you're modifying items that aren't working from the measurement stance, there's pros and cons to that. And if you're modifying from a predictive stance, meaning removing a latent variable, changing a predictive pathway, removing a moderator's pathway, those are very different implications when we start thinking about the pros and cons to that. So go back and reflect with this guy and some reflection questions. So pause, go back to your guide, spend some time on thinking about modifications. All right, up next, process and review. You're going to watch these videos a couple of times and really think through some things. Then you're going to get into reliability and validity in measurements. That's going to lead into the CFA work. I want you to go deeper with correlation and covariate matrices understanding. So correlation and variance matrices. And then we're going to get into the actual CFA learning, and you will have your CFA article dissection due next.